Okay, we are in the middle-ish to end of gases. And last time we talked about gases and some important gas laws and some relationships. Again, for us, there's three main units, an atmosphere, which equals 760 millimeters of mercury. And that also equals 760 torr. Once again, 1 torr is the same as 1 millimeter of mercury. So those really are, again, the three sort of common units that we have for gases that we come across. There are others, but these are really sort of the main ones. And that 760 number is important, as obviously that is the number we use to convert between the different units. So basically, if you have atmospheres and want millimeters of mercury or torr, you're going to multiply by 760. And if you have either millimeters of mercury or torr, you're going to divide by 760 there to get to atmosphere. Pretty much there's three variables that we've been talking about: pressure, volume, and temperature. And the gas laws relate to these guys. We saw our friend Boyle, perhaps. And Boyle looked at pressure and volume relationship holding together at constant temperature. And again, what we saw was as the pressure goes up, the volume goes down, and vice versa there. As the volume goes, the pressure goes down, the volume goes up. We also saw Charles' law here, and he looked at volume and temperature relationship of V1 over T1 equals V2 over T2. This was at constant pressure. And remember that really important here is the temperature. Pretty much in any gas law, it does need to be in Kelvin. Again, even if they give it to you in some other unit and want the answer in some other unit, it does need to be Kelvin when it does go into the gas law. The relationship we saw here is basically as the volume goes up, so does the temperature. And temperature goes down, so does the volume. Remember, in this situation, the volume's adjusting, and that is either giving the gas molecules more room to fly around or less room to fly around in, and that's what allows it to keep a constant pressure. So here with Charles' law, the volume does the adjusting, and that's how we're able to keep the number of collisions relatively constant and the pressure remaining constant. Very similar one to it is Guy-Lussac's law. And that is P1 over T1 equals P2 over T2. And that is at constant volume. So in this case, once again, as well, we need some Kelvin action there on the temperature. The pressures really could be any unit as long as they're the same, and same thing with the volumes on the guide to the left, as long as they are the same. But with this relationship here, because we do have that constant volume, the volume of the container will not adjust to allow the pressure to not change. So because of that, we do end up getting, in a higher temperature situation, more gas molecules flying around faster, which means more collisions, and more collisions results in an increase in the pressure. And opposite of that as well, if we lower the temperature, they're going to be flying around slower, less collisions, and we will see the pressure start to come down. We briefly mentioned Avogadro and his law as well. And Avogadro deals with volume and moles. V1 over N1 is equal to V2 over N2. This is actually at two different conditions, constant pressure and temperature conditions. And basically N here is moles. And as the number of moles increases, so does the volume, and vice versa. As it sort of decreases, so does the moles as well. So taking all these gas laws together, these are all ones where we have sort of a before and after type situation, a couple of pressures, a couple of volumes, maybe a couple of temperatures. We can put these together for an ideal gas law, which is PV equals nRT. That's our ideal gas law. And again, as we talked about at the end there, this is the most restrictive. That pressure has to be in, not that, that's liters. That's not really pressure. Try atmospheres would be better. Let's try that again. Here we go. So the pressure here does need to be in atmospheres when you use it. Volume here needs to be in liters. N is moles. T is Kelvin for our temperature. And the reason, again, all those guys need to be that is R is a gas constant. And that is a value that you should think that you always have available to you. So many times in problems, they're not going to like tell you, hey, R is this. They just assume that you know that you have R available to you. So you should always keep that in the back of your head. Once again, that's the common numbers used, and more commonly nowadays, 821 numbers okay as well. This also tells you the units that everybody else needs to be in, and that's why it's so restrictive here. And the ideal gas law is a little bit different than all the other ones. Again, there's just sort of one condition. So you got one pressure, one temperature, one volume. So no, kind of like a before and after type situation. I think that's where we laid up, I think. Yeah. Any questions on any of those there? Yeah. They're, yeah, they're basically proportional to each other. So as one goes up, so as the moles does. We did stoichiometry, right, where we did mole to mole relationships in an equation. You basically can do volume to volume relationships the same way if you're dealing with an equation that has all gases at constant pressure and temperature. So just like we could say, hey, there's 2 moles of this reacts with 2 moles of that. The same thing, we could say 2 like liters reacts with 2 liters of that. So they're kind of identical in that sense. They're sort of proportional to each other. Other questions? All right, so let's continue on then here in our journey. So we're talking about the ideal gas law and a couple other important things. First off, we'll start with this. STP stands for standard temperature and pressure. So in a problem, when they actually say, what is it at STP, or this is being done at STP, they're actually giving you both a temperature and a pressure value. So when it says STP, the temperature is basically 273 Kelvin, and the pressure is 1 atmosphere. So if you see something that says at STP or something of that nature, and you're like, well, there's no real numbers, those are the numbers that you should use for both the pressure and the temperature in that situation. Now, there's a nice relationship that you could use when you are at STP and only when you're at STP conditions. And it's a relationship that can allow you maybe not to have to use the ideal gas law in a certain situation. So when you do have, and when you are at STP, and only when you're at STP, if you take 1 mole of any gas, that will equal 22.414 liters. So what that allows you to do, as I just mentioned, is if you happen to be at STP conditions, you might not have to plug things into the ideal gas law. You could use that as a conversion factor. If you know the moles, you can find the liters. If you know the liters, you can find the moles. Again, with sort of bypassing the ideal gas law. You can only use that relationship if you're at STP. So it has to be a temperature 273, has to be a pressure 1 atmosphere. If you are not exactly at those conditions, you should not use that conversion for sure. The good news is you could use the ideal gas law in any condition, STP conditions, non-STP conditions. You could just throw the values into the ideal gas law. So even if you're at STP, you could just put those values in for temperature and pressure, and it comes out the same. So if you don't want to worry about this relationship, I can save you a little bit of time occasionally. Thank you. You could always just go into the ideal gas law and use that no matter what the conditions are. So ideal gas law, you can use it in any conditions. That relationship I just circled, it must be standard temperature and pressure conditions for you to use it. Otherwise, you should not use it. That is also how we get to the gas constant value. So if we solve the ideal gas law for R and put in that we have 1 atmosphere, temperature is 273, volume of gas would be 22.414 liters in 1 mole. That's basically where that gas constant value comes from when we put it in there. Any questions on that there? Okay. So let's take a look at one, I think. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a container that has 5.43 liters at 69.5 degrees Celsius. Let's see what you come up with here. Okay, so let's take a look. So once again, as we talked about last time, especially when you're dealing with gas problems and gas laws, it's a really good idea just to pull out the information and sort of label it. And oftentimes it will kind of point you in the right direction if you're not sure maybe what gas law to use. So in this case, we are looking for a pressure. We have 1.82 moles, which is N. We have a volume that is 5.43 liters, and we have a temperature there that's 69.5 degrees Celsius. So clearly here we have one of everything. You can maybe kind of see the ideal gas law there would be the appropriate one to choose. And that PV equals nRT would be the right one to choose. Again, we have no two pressures, volumes, or anything like that. So none of the earlier gas laws would work in this situation. Remember, that also means much like this problem, they don't give it to you, but you always have the value of R sort of available to you, which is a constant. In terms of units, everything's good except for our temperature. We do have to convert our temperature there into Kelvin. So we're going to do a little 273 action on it. Going to give us 342.5 Kelvin. We now have everything where we need. We are looking for pressure. We're going to move this to the opposite side, which means it's going to end up on the bottom. We're basically dividing by V to the other side. That will give us P is equal to nRT divided by V. Put it in our numbers in the correct locations. We got 1.82 moles. We got 0.08206, our R value here. We have our temperature that we converted into Kelvin, all going to be divided by our volume here, which is in liters. And now our units will cancel. Moles, Kelvin will cancel, liters will cancel, and that's going to leave us atmospheres up on top, which is good because that is what we're looking for, pressure. And 1.82 times 0.08206 times a 342.5, hit equals, divide by 543. We're going to go with a 9.42 atmospheres as our pressure in this case. Any questions on that? Yeah. Mm-hmm. So what are you talking when we do the temperature conversion? Yeah, when we do the temperature conversion here, remember that when we do temperature, we want our converted value to look like the original one. So in this particular case, it is to the first decimal place. So all we're doing in that case is just converting the units to another one. So we would want to keep it to the one decimal place in that case. Yeah. So you probably wouldn't want to round it in that particular case. So, yeah, question? Well, that's one of the reasons. So if we think about, just quickly scanning all the sort of other gas laws that maybe you could have potentially used. And all of those other gas laws, there's basically two pressures, two volumes, right? Two temperatures, something like that. And in this case, we obviously have just one of everything. So really the PV equals nRT is really the only equation where you kind of have one of everything. And you could kind of almost see it here. You got PV and T, and you always have R. So, you kind of have, and you have N, I missed there as well. So it kind of shows you that that's probably the one that you should use. Yeah. Especially when you have a situation where you don't have twos of everything, or at least a couple of the same sort of values. Other questions? Now, variations on this problem, in addition, obviously, the temperature that you have to convert to Kelvin, very commonly as well. Instead of giving you moles, you may be given grams of something. And like we did in previous chapters, we could use the molar mass from the periodic table to take it to moles. So that's, again, something that's very commonly sort of done as well in these type of problems. Any questions on that one there? All right, then let's take a look at another gas law, because why not? Feel like we have time for that. So if we take the ideal gas law and actually solve for R, which is a constant, we could actually put each of these things together for two different conditions. And that gives us something like P1 over P1 V1 over N1, T1 equals P2 V2 N2 over T2. And usually in a gas situation, the number of moles will also remain constant unless you pop the lid open or something like that. So they're all flying around in usually a closed container. So this oftentimes will reduce down to a gas law that we commonly use. And this is sometimes referred to as the combined gas law. And it looks at changes in all three of those variables. P1 V1 over T1 is equal to P2 V2 over T2. Once again, here with this particular one, pressure and volume, the units really don't matter as long as they are the same. And like any other gas law, though, we do need Kelvin, obviously, on the temperature, like usual. So this one is the one that gives people, again, a little hard time sort of rearranging. So once again, you could just do opposites, right? If you move across the equal sign, and help you hopefully rearrange it correctly. So this is a really good gas law. So why is this a good gas law? Well, you want to invest your time in learning a gas law. I would go with this one. This one seems like a good one. So the reason I say this one seems like a good one, let's go back a couple pages here and we'll talk about why that is. So if you remember the combined gas law, if you had to choose out of our big list of gas laws, P1 V1 over T1 equals P2 V2 over T2. You could pretty much get all the other gas laws from this gas law. So if you remember this one, if you think about Boyle's law, that's at constant temperature, right? So basically you just scratch out temperature and hey, look, there's Boyle's law right there. If you take this combined gas law and you're looking at a Charles law situation, that is at constant pressure. So you scratch out the pressure. Hey, look, there's Charles law right there. If you take this gas law and you got a Guy-Lussick type of situation where you have constant volume, scratch it out. There's that gas law. If you invest the time and you remember this gas law with the moles, for example, and it's at constant pressure and temperature, which is Avogadro, you just scratch them both out. And there's Avogadro's law. So you can remember the combined gas law, which is this one, basically. And whatever is constant or whatever is not given to you, you could just scratch it out and you'll have the gas law that you need, which means basically, if you learn this gas law here and your ideal gas law, you're pretty much in business for all the gas laws you would ever need in this class and probably most classes that you take. So it's a really good one. It has everybody in there. And again, anything that's constant, anything that's not given to you in the problem, you just scratch it out and you'll find the gas law that you need to use. Any questions on that there? All right. So now let's try using this one when we need to use it. All right, so let's give this one a go, see what you come up with here. We have a sample of oxygen gas at 27 degrees Celsius in a volume of 9.55 liters, pressure 2.97 atmospheres. If we change the pressure to 825 atmospheres and it's heated to 125 degrees Celsius, what will be the new volume? So see what you come up with on this one. Bless you. Okay, let's take a look and see. So once again, I'm just going to pull out the information. We have obviously a temperature here that is 27 degrees Celsius. We have a volume that is 9.55 liters. And we got a pressure there that is 2.97 atmospheres. The pressure is changed. So we got another pressure here of 8.25 atmospheres. We have another temperature of 125 degrees Celsius. And we are looking for a volume. So again, clearly here, you should hopefully be able to see pretty much this is going to be our combined gas law. It's got all three of those variables listed. And this is really the only one that has all those three kind of together and twos of each of those things. Doesn't matter which one we list as ones and twos, it doesn't. So usually just how it's written in the problem. So I'm just going to call these guys the twos and these guys the ones. In terms of the pressure, we're okay. They're both in the same unit, but like normal here, we're going to have to do some conversion of our temperature. So we'll add a 273, going to give us 300 Kelvin. We'll also add a 273 there, 398, I think. All right, now we got everybody there. We're looking P1, V1, T1 equals P2, V2, and T2. In this case, we are looking to keep V2 by itself up on top, so it's already there. So really all we have to do is move everybody else to the opposite side. So this T2 is on the bottom, which means when I move it over, it's going to end up on top. And my P2 is going to end up basically on the bottom here. I'm basically multiplying both sides by T2 and I'm dividing by P2 to the other side. When I do that, I'm just going to write it in order, P1, V1, and now my T2 ends up on top, my T1 and my P2, and that leaves me only V2 on the other side, which is on top and what I'm looking to solve for. So once again, we're multiplying basically the T2 to both sides, so they cancel, and then we're dividing by P2 to both sides so that they cancel is essentially what we're doing there. Any questions on that? So also really important, now that we have it rearranged, we put everybody in the correct spot. So we're going to go with our P1, which is 2.97 atmospheres. Our V1, which is 9.55 liters. Our T2 should go up on top, which is our 398, divided by our T1 that should go on the bottom, which is 300 Kelvin, and our P2, which is 8.25 atmospheres. The atmospheres will cancel, the kelvins will cancel. That's going to leave us liters up on top, which is a good because that's a volume. So we're going to take 2.97 times 9.55, too many fives, times 398, hit equals, divide by 300, hit equals, divide by 8.25, hit equals. It's going to get us 4.56 liters in this particular case. Any questions on that there? Okay, so again, this is the one that I say gives people a hard time rearranging. So if that is a issue, take some time to make sure you understand how to properly rearrange it. It is really, really common. People sort of inverse numbers and put them in the wrong spot and stuff like that. Typically, whatever you're solving for should end up on top. Yeah, so we're solving for V2, so it should end up on top. And that's why if we were solving, for example, for T2 here, we would actually need to move T2 to the other side and bring everybody else back over to the other side so we could get to the top. So you always want to make sure that whatever you're solving for ends up on top by itself. Otherwise, if you do it on the bottom, that's 1 over that, and it's the inverse of it, right? Any questions on the combined gas law? All right. So the next thing we're going to talk about is the idea of partial pressures, Dalton's law of partial pressures, which sounds really difficult, but it's not too bad here. So when we have a gas in a particular container, and let's just say we only had gas A in this case, flying around, the pressure of this container, the total pressure of this container, is basically going to be only the pressure exerted by gas A as it's flying around and banging into the walls or whatever it may be. But very common, gases come in mixtures of different gases. Like maybe we got gas A flying around, gas B, I'll try the alphabet there, gas C going around. And in this particular case, in a mixture of these three gases, the total pressure is actually equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C in this particular case. And these are what are referred to as partial pressures. They partially contribute to the overall pressure of that mixture. So there are a couple of ways that you could calculate the partial pressure, but most commonly the partial pressure is calculated using the ideal gas law, P equals nRT, where you solve for P, which would be nRT divided by V, and you basically solve for P for each of the gases individually. And we could do that because even though they are all flying around in the same container, and I think we touched upon this last time, this is an ideal gas situation, which means they're not going to interact with each other. So we could almost think of all these gases as being in there by themselves, even though they're really not. There's going to be no interaction between gas A and gas B or gas C that's going to affect the pressure in an ideal situation, which is what we're assuming here. So we could actually just do three separate calculations for each of the gases and solve for P for each of them. And that would give us the partial pressure of each of the gases. And to get the total pressure, we would just add up all those partial pressures together. Now, one of the nice things about this is because they are in the same container, the volume of that container is going to be the same for all the gases because they're flying around in the same container. And most likely that container is sitting in the same room that has the same temperature, will be the same for all the gases. So in a partial pressure situation, pretty much the only thing that would probably vary when you use the ideal gas law between all your gases is the moles. So you may have different moles of gases flying around, but the temperature will be the same for all, in this example, three gases. The volume would be the same for all three gases, and obviously R is a constant, so that would be the same for all three gases. So really the only thing that you typically have to find for each gas is the number of moles, and then you can again go into the ideal gas law separately for each of them, and that will get you your partial pressures of each of those gases. Any questions on that there? And that's basically what this is showing here. We can, again, just however many gases you got going on, you basically just keep using the ideal gas law and solving for P for each of them. And again, you add them at the end. So that's also important. Again, you add each of the partial pressures, don't multiply or anything crazy like that. Just add them together and that'll give you your total pressure as well. So let's take a look at one maybe here. Let's say we had a mixture of helium gas and neon gas in a 2.5 liter container at 27 degrees. What is the partial pressure of each gas? And what would be the total pressure? So why don't you give it a go? Let me give you a couple of numbers that might help. Helium is 4.003. And we got neon going on there. Neon is 2018, we'll go with. I think that's what that says, 2018. All right, so we basically got, again, in this situation, we got some helium flying around. We got some neon flying around. You're looking for three answers: the partial pressure of helium, the partial pressure of neon, and what will the total pressure of this mixture be? So give it a go. Maybe an ideal gas law for everybody. Yeah. Okay, let's take a look. So again, we have both of these gases basically contributing to our total pressure in this case. So in this case, the total pressure should equal the partial pressure of helium plus the partial pressure of neon in this case. And again, in this situation, we want to probably go an ideal gas law for each of these guys. And again, solving for P in each of these cases. So let's just take out our information that we got going on. We got 5 grams of helium. We also have 5 grams of neon. We have definitely a temperature that is 27 degrees Celsius. Since we know it's a gas law, we do know, hopefully we do need to convert that. So that's going to be converted into Kelvin for sure. It's going to be 300. We also have a volume that is 2.5 liters. And remember, since they are basically in the same container, they have the same volume and they have the same temperature. So that's going to go for both gases. So once again, we have temperature, we have volume. R is always, we have that available to us, which is a constant. And that means that really the only thing we're missing to be able to solve for our pressure of each of these gases from the ideal gas law are the moles. So really at this point, it's going to be a conversion from grams to moles using the molar mass from the periodic table like we've done before. So we'll start with helium. And again, that represents that there are 4.003 grams per mole is the molar mass of helium. And we're going to use that as a conversion factor. So we'll go opposites here. We got grams on top. We'll go with the 4.003 grams per mole for helium. We'll do a similar calculation here for neon, which we could grab off the periodic table as well. And that would be 20.18 grams per mole of neon. The grams are going to cancel for both of these guys. And that will give us our moles, which are here. Looks like 1.25 moles for helium and 0.248 moles there for our neon. Any questions on those calculations? So at this point, we now have really the missing moles that we need for everybody. So we're just going to, again, go into the ideal gas law separately for each gas and just solve for P. So if we solve for P for helium, that would be nRT divided by V. So putting in our numbers for helium here, we're going to use the moles for helium, 125. We're going to use our gas constant, which we always have. We're going to use our temperature, which we've converted to Kelvin. We're going to divide it by the volume, which is the same for everybody here. Liters will cancel, moles will cancel, Kelvin will cancel. Going to leave us atmospheres as the only unit that's left, which again is good since we're looking for a pressure. That's a 1.25 times 0.08206 times 300 divided by 2.5. And we'll go with a lovely 12.3 atmospheres. That number represents the partial pressure of helium in this mixture. So that is basically the pressure that helium is supplying to this mixture. We're going to do the exact same calculation, except obviously in this case here, we're going to do it for neon, which would be nRT over V. Really, the only change is going to be we're going to use the moles of neon in this case, obviously. So we're going to use 0.248 moles of neon. We got our 0.08206. Still the same temperature because they're in the same spot. And still the same volume because they're also in the same spot. Once again, our moles cancel, Kelvin cancel, liters cancel, leaving us our atmospheres there up on top. And that's going to get us 0.248 times 0.08206 times 300 divided by 2.5. And that's going to give us a 2.44 atmospheres. And that is considered the partial pressure of neon in this mixture. Any questions on either of those calculations? Now, the total pressure is found by what should I do with those two numbers? Yeah, so I just need to add both of these numbers together to get the total pressure of that mixture. And that would be a 12.3 plus a 244 and 14.7 in this case, atmospheres. Any questions on any part of that calculation? By the way, which one is the major contributor here to the pressure of this mixture? It is helium by a long shot. Any ideas why helium is the major contributor? It has to do with these numbers. Which one is lighter? Helium is much, much lighter. So it has a much higher velocity, which means it's flying around a lot faster than the heavier moving neon, which means it's going to create more collisions and more pressure. So that's why we see here in this case that it's actually contributing more pressure than the heavier, slower moving neon in this case. One's like 600 miles per hour, one's like 1800 miles per hour. That's how fast they're moving. Any questions on partial pressure or this type of partial pressure problem? So really it's just an ideal gas law where you kind of do it for each gas separately and then add them together to get the total pressure. Obviously, if you're given the total pressure in one of the partial pressures, you could kind of figure out the other one by just subtracting and stuff like that. There's also another situation where partial pressures come into play, and let's talk about that situation, similar to that lab you probably did. Terrible lab that you maybe did. That twistle tube that probably braked. Did it break? Nobody broke their tube? That's very impressive. Very good. All right. So in this particular case, we got a little potassium chlorate and some of our manganese dioxide there, are really manganese 4 oxide as our catalyst. And if you didn't put a lot of that in there, you probably had a long afternoon that night if you didn't put a lot of that in there. We're going to heat this up, and that's going to decompose this basically into a little KCl and some oxygen gas. That oxygen gas got nowhere to go. And it's going to go into this container, and basically this container is filled with water. It's going to displace the water, and this empty spot here is actually where your oxygen gas will basically end up in your collection container. But because this experiment, we are collecting the gas in water as a result of the experiment itself, we get a little bit of heat from an experiment in water. Heat in water also produces water vapor or water gas. So we actually get a mixture of two gases in that empty space. One is the gas we're actually interested in this example, oxygen. The other one is really just a byproduct of how you collected the gas, and that water kind of comes in there for the ride. So in this situation, we have the total pressure of this mixture is really the pressure of the gas you're interested in, plus the pressure of water, and this is what is sometimes referred to as the vapor pressure of water. And a lot of times when you do an experiment like this, this is a value that you could look up in a table based off of the temperature. So you look up this value in a table, and because we're not really interested in the water aspect of this, we're really interested in this case, the oxygen that we're collecting. You could rearrange this and solve for the pressure of the gas would be our total pressure minus the vapor pressure of water. So it's almost like a correction calculation that you sometimes do a lot in the laboratory to subtract off the pressure contributed by water. Sometimes people refer to it as like the pressure of the dry gas because you subtracted off water or something like that in this particular case. So this type of thing, whenever you collect a gas and water's involved, you usually have to do this correction calculation to get rid of the pressure that the water is contributing because you're not really interested in it. The good news is it's really usually just a subtraction one. In the laboratory, your total pressure would be the barometer reading for today. In the book, they would probably give you the total pressure somewhere in that question. So as you can see here, basically it's just your total pressure is the pressure of that vapor pressure of water plus the pressure of the gas that you collected. The key words usually when you have a problem like this is it will say somewhere like the gas was collected over water, or it'll say something like it was saturated with water vapor or something like that. Those are like the keywords of like, I should probably do this little subtraction from my total pressure to get the pressure of just the gas by itself. So if we take a look at one, for example, here, the sample of oxygen gas is saturated with water vapor. So right there is the keyword I was just talking about, or phrase that's very commonly sort of used. And that tells me that I'm collecting this gas over water, and along for the ride is some water with the gas that I'm trying to collect. The total pressure is 753 torr. Whoops, come back. And the vapor pressure of water at 30 degrees is 31.824. What is the partial pressure of oxygen? So this is that partial pressure situation we were just looking at, the pressure of our gas we're interested in, plus the vapor pressure of water. In this particular case, they gave us the total pressure, which is 753 torr. The pressure of the gas we're looking for, which is really oxygen in this case, plus the vapor pressure of water. So if this was not provided to you in a problem, there's usually a table in the gas chapter of vapor pressure of water where you could go look it up based off of the temperature. So obviously this was done at 30 degrees Celsius. We would go to the table and look up 30 degrees Celsius for the vapor pressure of water, and that is the number that we would find there, which in this case is 31.824 torr. That means that the pressure of the oxygen gas in this case, we're going to subtract this to the other side, is 753 torr, which is our total pressure, minus the vapor pressure of water in this case. And if we do that, we will end up with 753 minus 31.824. Gets us, we'll go 721 torr in this case. That would be the pressure of just the oxygen gas itself in this mixture. And that is, again, what you're probably interested in if you did this experiment. You're, again, not interested really in the water part of it. We also want to convert to atmospheres, which means I should do what with that number? Should divide by 760, something like that. Yeah, 760 torr is an atmosphere, right? So that will convert me into atmospheres. So a little 721 divided by a 760-ish, 0.949 we'll go with 0.949 atmospheres. This would be considered the partial pressure of oxygen that you collected, and or the dry oxygen gas pressure as we subtracted off basically the water's contribution. So this is another sort of partial pressure situation. It's not too bad. It's really just adding or subtracting, depending on which way you're going. Most of the time, just subtraction, where you basically take off the contribution there from water. And those are the key words that you know you have to kind of do. That is, again, I'll mention something like you collected it with water, saturated with water vapor, something like that is usually the keywords in those type of problems. Any questions on partial pressures here? All right, to finish up this chapter then, the kinetic molecular theory of gases are these parts. And we talked about a number of these sort of things along the way. And let's talk about what these different parts are, and also, you know, what makes it an ideal gas. So gases, as we talked about, consist of tiny particles. They can be atoms or they can be molecules. These particles are so small compared to the distance between them that the volume itself of the individual gas molecules are assumed to be zero and negligible. And that number two is, again, one of the things that make most of the things that we deal with an ideal gas. And as we talked about, I think last time, if you look at most of these problems, we again talk a lot about the volume of the actual container that the gas is in rather than the volume of the gas itself. So under ideal conditions, normal sort of pressures and temperatures, that sort of situation holds true. Is more important the volume that they're flying in rather than the volume of the small little gas molecules themselves in an ideal situation. The particles are in constant motion, colliding with the walls of the container. Again, these collisions is what we assert the pressure. So the more collisions that we have, the higher the pressure that we would assume, and vice versa. Obviously, the less collisions that occur, we would have lower amount of pressure. Number 4 is that particles are assumed to not attract or repel one another. That is the other thing that really makes something an ideal gas. So in an ideal situation, even though, as we just saw in the previous example, where we had multiple gas molecules flying around in the same container, in an ideal situation, they're not going to interact with one another. And that will have no effect on the pressure. So that's why we can do a calculation like we did in that problem, where we could just do the calculation for each gas separately, even though they're all flying around the same container. If they actually did interact with each other, it would have an effect on the pressure, was one of the things it could have an effect on. Because if you did have a gas molecule, for example, flying this way, but there's another gas molecule that maybe it's attracted to, or maybe it's trying to get away from, that's going to either slow it down or make it go quicker, and that would affect the collisions that you would have. So we don't worry about that in an ideal situation. There's no real interaction between any of those gas molecules. Lastly here, the average kinetic energy of our gas molecules is proportional to the temperature in Kelvin. So again, as we increase the temperature, our gas molecules should be flying around faster. And as we lower the temperature, they should be flying around a lot slower. And just to touch on a lot of those gas laws that we talked about in the relationships, again, at higher temperatures, we do see those gas molecules moving faster, which we would probably mean that we would have perhaps more collisions, especially if the volume doesn't adjust. And at lower temperatures, they would be flying around slower, which would mean we would have less collisions and lower the pressure, again, if the volume does not adjust. If the volume does adjust, as we talked about with Charles' law, as that temperature increases, the volume is again going to increase with it to give everybody more room to fly around in, and vice versa. If you lower the temperature, the volume is going to decrease to maintain that constant pressure. Any questions on gases? Yeah, so any gas is considered an ideal gas. An ideal gas really is how any gas basically behaves under normal sort of temperatures and pressures, like temperatures of like we have now, like 25 degrees Celsius, 1 atmosphere. When we get to really high pressures or really kind of low temperatures, those gases behave more like what I refer to as real gases. And you do have to take into account like the volume of the gas itself. You do have to take into account how they interact with other gas molecules. It actually turns the ideal gas law into a super scary equation. There's known as the van der Waals equation. So there's a lot of factors that you factor into that. But in order to get that to happen, you got to have like super high pressures, like 600 atmospheres. This is way more than 1 atmosphere is like where we hang out. So anywhere around 1 atmosphere, even a little above or a little below, they don't really deviate that much from ideal conditions. So we sort of think about everybody being in ideal conditions. But if you did happen to have something that's really high pressure or really low temperatures, then they become more real gas, and you have to take those into account, which will never happen in this class. So if you take a neurochemistry class, maybe it'll happen, but not this class. Any other questions on that? So to answer your question, any gas, basically, it's more like how a gas is behaving rather than this gas is an ideal gas or nothing. Other questions? Off to solutions. All right, so this is chapter 9, solutions. So let's talk about solutions. And most good talk. Most biological reactions happen in a water environment or aqueous environment. I think we might have talked about it previously, but aqueous is basically the guys that have that abbreviation next to it. It means a water environment. It's really a solution. So all solutions are aqueous, and solutions are, if you remember back to whatever chapter that was in, they are really homogeneous mixtures. So that is basically what a solution is. A homogeneous mixture is one that looks the same throughout. And there is a difference between aqueous and something that has the L symbol next to it, which is a liquid. A liquid is something that's a pure substance. So for example, if you had water by itself, that is why it gets the liquid designation there. It is a pure substance. A solution is really made by taking something like water, a pure substance, and mixing it together with something else, like say salt with sodium chloride. When you mix that together, the salt's going to dissolve in the water, and you will end up with a sodium chloride that is a solution that gets the aqueous symbol. They're both obviously in the liquid state, but only things that are pure substances by themselves will have the L next to it. If you see the aqueous, basically it's a solution. That's what all those dropper bottles probably are of reagents that you've used in the lab. They are all basically solutions. A solution is basically made up of two parts. There's the larger part, which is the solvent. Start that way, I guess. The solvent is the larger part of the solution. And the solute is the smaller part of the solution. So in my example here, the water is our solvent, which is a really good solvent for a lot of things that are ionic and polar. It's actually a pretty crappy solvent for other things that are non-polar. So water is a very good solvent for a lot of things, but not always the solvent of choice for everything. And we'll talk about that in this chapter as well. Sodium chloride here would be our solute. How do you know what the solute is in a solution? It's pretty simple. It's the name of the solution. So if I have a sodium chloride solution, sodium chloride is your solute, and probably water is your solvent. If I have a hydrochloric acid solution, hydrochloric acid is the solute, and water is probably the solvent. Water is probably the solvent for most ionic compounds. And again, the name of the solution is really the solute, and probably most of the time, but again, not 100% of the time, water is probably the most very common solvent that you could have. You do need both of those things to make a solution. You got to have the solute and the solvent together. There we go. Here in this case, waters are solvent. Copper 2 sulfate is our solute. Obviously, before it dissolves, that ionic compounds together. And as it starts to dissolve, we end up with a nice solution here of ions flying around. How does it dissolve? Well, in an ionic compound, we have positive ions and we have negative ions, which are our cations and anions. And if we use water as our solvent, water is polar, if you remember from bonding. Oxygen is more negative, right? Hydrogen side there, more positive. So what happens when you go to dissolve something, the negative side of water will surround the positive ion. And the positive side of water, which is the hydrogen, will surround the negative ion. And that does two things. That is pretty much what allows it to dissolve. And it also keeps those ions away from each other, because probably the strongest attraction you could have is those two ions wanting to get near each other. It's as strong as you could have. But there's so much water in there, they're able to pluck off those ions from one another. And those water helps it dissolve, helps keep those ions away from it, also helps it disappear so we can't see it anymore, right? Is still there. This is just a physical change, because what would happen if I heat up that solution? All the water will go away, right? And now there's nothing to stop those ions from coming back together, and you would see the solid reappear. So sometimes people think when you make a solution, it's like a chemical change. It's not. It's actually a physical change. And that's why it's a homogeneous mixture, right? And those are physical changes that occur. And we just can't see it anymore because there's just a sheer amount of water in there that is no longer visible to us to see those guys, but they are definitely still there. So if you ever evaporate off water from a solution, you'll be left with a solid residue that was dissolved in that solution. And again, that's basically both parts of the solution, both parts of the mixture retrieved. So as I mentioned, water is a really effective solvent because it is polar, and it works really well for ionic compounds as it can surround them, like I just drew a second ago. So water works really well for polar molecules as well, because they can interact the same way. Water works really bad for non-polar molecules. So when we talk about solubility and things sort of mixing together, there's this idea, as we'll talk about, of like dissolves like. So things that are polar and polar work really well together. Things that are ionic and polar work really well together, and that is why water, which is polar, works really well with an ionic compound, because they're basically opposites attract, so they're able to interact well with each other. Polar molecules together will mix well because they can use the same type of intermolecular forces that they use with themselves. Intermolecular forces are the forces that one molecule uses to hold together with another molecule. So if they come across somebody that uses the same type of interaction they use with themselves, they mix really well together. Even nonpolar things and nonpolar things mix really well together because they also are using the same type of sort of forces as they use with themselves, they could use with whatever they're trying to mix with. You only really run into trouble when you try to cross over something that is nonpolar and polar. No good. Yes, they really don't mix and stuff like that. So that's why we use water with a lot of things, because a lot of things are polar, a lot of things are ionic that we want to make solutions with. So it works really, really well because they can interact. All molecules, believe it or not, polar molecules, non-polar molecules, how all molecules interact with themselves, with others, is a basic interaction of opposites attract. Yeah, so they have, like, a positive side of one molecule is attracted to the negative side of another, and that's what we see here with our ions. The positive ion is attracted to the negative side of water, and the negative ion is attracted to the positive side of water, and that's ultimately, it boils down to how all molecules basically interact with each other is through electrostatic attraction. Positive and negative attraction is what keeps them together, and when they don't have that option, they don't mix really well. So that's also why, as we'll talk about later on in this chapter, why something like oil and water don't mix really well, because they're using different types of interactions. Here's a picture. As you can see, just the amount of water coming in. That is what an ionic solid looks like. It's a bunch of ions basically together by the opposite attract. Waters come in and start plucking off ions. You help it along because when you make a solution and you want to dissolve something, you typically do this, right? You stir it. So you're splashing water all over the place. You're also adding energy, right? Which helps the process of everybody starting to pluck off of the solid and helps it to dissolve. Here's another picture in case you didn't like that picture. Here's a third picture in case you didn't like the second picture. I think I'm out of pictures at that point. So let's talk a little bit about solubility in water. So if something is soluble in water, that means that basically it will, if it is a solid, it will dissolve in water. If it is a liquid and it's soluble in water, what will happen? They will mix, right? And you will not see different layers, right? And obviously, if you have a solid, it will dissolve into the water. If you have something that's insoluble, the solid will not dissolve in water or whatever it may be. And if you had two liquids that are insoluble in each other, you would start to see layering happening, right? That's sometimes referred to when you talk about liquids and mixing, miscible if they mix and immiscible if they do not mix, so kind of soluble and insoluble. So as I mentioned before, things that are ionic are definitely soluble in water because they could do that kind of opposite, positive being surrounded, positive ion being surrounded by the negative side of water and vice versa for our negative ion. But there are some non-ionic substances like sugar and ethanol, which is also soluble in water. And the reason why something like ethanol, which looks like this, I'm going to pull my organic out here. Here we go. Organic preview, maybe. This is ethanol and what it looks like. And really, it's an organic molecule, and it has basically two parts. It has this part back here, which is all carbons and hydrogens. And if you remember from bonding, carbon-hydrogen bond is non-polar, yeah, which means equal sharing electrons, no positive side or negative side. But it does contain this OH group here. And that OH group, if you do the difference in electronegativity, is a polar bond. So this guy is polar. That means the oxygen is more negative, the hydrogen is more positive. So that works really well when water comes rolling by, which is also more negative here, more positive here. The positive hydrogen and water are able to interact with one another through opposites attract, and something like ethanol will be soluble in water, even though it's got a little bit of a nonpolar part. We will talk about in later chapters as well, though, if this nonpolar part, you start adding on more and more carbons, solubility drops a lot. So these are around 5 or 6 carbons, no solubility, but stuff before 5 or so carbons, it will be relatively soluble in water. And that's because it has that OH group. What happens when you build out this side of it and it gets bigger and bigger, the nonpolar part, that little OH group has a very hard time finding the water, and the water has a hard time finding itself. The nonpolar part gets in the way. It's what's sometimes referred to as steric hindrance. It doesn't allow the water to kind of get in there very effectively. And it's got this big nonpolar part that's not going to work well with water to begin with, and it starts to lose its solubility. Sugar is a little bit larger of a molecule, but if you've seen sugar, which we'll take a look at a picture here, it's pretty much littered with OH groups all over it. So everywhere there's an OH group, it gives it a place to interact well with water, makes it quite soluble. This is methanol, and methanol can interact with water. And this bond here is what is referred to as an intermolecular force. And that is the force that holds 2 molecules together. And specifically, this is what is known as hydrogen bonding, which is the intermolecular force choice of water. Water wants the hydrogen bond. In order for something to hydrogen bond, you need to have a bond between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine. So in this case, there's our oxygen and our hydrogen bound directly to each other. So water is able to hydrogen bond. Same thing here in methanol, oxygen, hydrogen bound next to each other. The reason that is, if you look on the periodic table, NOF, right, is your highest electronegativity, right? Up and to the right on the periodic table, that is that way right there. So because those guys, when they are bound to hydrogen, will create a pretty good polar bond, a good separation of charge, a positive side and negative side, that allows it to do that hydrogen bonding. Not all things that have hydrogens are able to hydrogen bond. For example, something like methanol here, or methane would be better. Methane here is a nonpolar bond. And even though it's got 4 hydrogens, good luck, it ain't going to do anything. It actually cannot hydrogen bond. So just because something has a hydrogen doesn't mean it could hydrogen bond. It has to have a hydrogen that's directly attached to one of these 3 elements in order for it to participate in hydrogen bonding. Something like methane cannot hydrogen bond, but it uses what is known as dispersion forces, which is pretty much the weakest as you could get in terms of interaction between molecules. It's the weakest type of force. And that is why when you take something that's nonpolar, it wants to use what is known as dispersion forces to interact with. And when you take something that has water to interact with it, it wants to use hydrogen bonding. And they're like, that's not going to really work over the long period of time. It will work for a very short period of time, but over the long period of time, they'll just separate out from each other. I sometimes think of like oil, vinegar, salad dressing, right? You can mix this for a short period of time, but when you leave the bottle sitting, everybody separates out because they can't maintain that interaction over a long period of time. Vinegar is polar, oil is non-polar. Just like when you get oil spill in the ocean, right? The oil starts to float on top because it can't mix anymore with the water over that long period of time. So things are typically soluble in each other when they are using the very similar types of interactions that they use with themselves. And their similar size also is really important as well. So if you get things that are different in sizes, it does make for some trouble sometimes. There's our ethanol hydrogen bonding. So as I mentioned before, our oil will not really mix with water. And that's because oil is pretty much nothing more than a super expensive long chain of carbons and hydrogens like gas, which is like octane, which is 8 of these together. Yes. So this is basically oil, super long chain of nothing but carbons and hydrogens, nothing found there but basically non-polarness all over. So it's a really large molecule. It wants to use dispersion forces. Once again, water wants to use hydrogen bonding. And really, for anything to dissolve in water, you got to think about what's happening first before you put anything in water. There's a bunch of water molecules that are basically attached to each other. So you basically got to break away some water molecules from each other and create a hole that allows something to come in. And if you get something like oil, which is really, really big, not interacting the same way, it just doesn't fit. So it works a little bit, but cannot really work very well. I relate it to like a garage. You know, you can put your car in there, it fits pretty good. You put a semi truck in there, maybe you get part of it in, but it's just probably not going to fit very well in the garage, right? A lot of it's going to hang out. It's not going to work very well. It's kind of the same idea, just too big, not using the same interactions. They're not going to be able to interact well with one another. So that is the idea of, as I was saying earlier, like dissolves like. So once again, anything that is polar and polar you're putting together, you should have no problem. They should mix. Anything that is ionic and polar, if you put it together, should work. Anything that is non-polar and non-polar should be good to go. But once again, if you cross over polar and non-polar, you're going to have trouble. They should not be soluble in each other. How do you determine polar and non-polar? It's all about that bonding stuff that we talked about in the bonding chapter. Is that molecule polar or non-polar? And those are the things that you have to kind of look at and determine, you know, if you're not sure if it's polar or non-polar. So up here is sugar, and although it's a relatively big molecule, like I said before, it is pretty much littered with OH groups, and everywhere you see an OH group, it gives places for water to interact with each other, and it makes it really, really soluble in water. And again, here's pretty much oil, where we do not see any of that happening. And that is typically what we do end up seeing again over a long period of time. They're going to basically separate out from each other because of the differences in how they're trying to interact with one another. So when we talk about solubility, when one substance dissolves in another, when the solute dissolves in the solvent, it is said to be soluble. So if we take a salt, which is like sodium chloride or an ionic compound, we would again expect it to be soluble in water because of the way it can be surrounded by water. When one does not dissolve in each other, it's said to be insoluble. There is a limit to the solubility of one substance in another. Gases are always soluble in each other, and that's because gases are pretty much flying around. So if you got multiple gases, they're just by the presence of them flying around are going to be mixing with one another, and they would be soluble with each other. Some liquids are also soluble in each other, and again, that's their polar and polar. Your non-polar guy is going to be soluble in one another. So how do I know if I mix some things together, will I get a solid to form or will I not get a solid to form? We could use what is referred to as solubility rules to help us make that decision. And this is a table of solubility rules. And first off, though, if something is soluble on this table, that means that is basically a solution. Everything should dissolve. And that is those guys that have the aqueous symbol when you look at an equation. If something is insoluble based on solubility rules, those are guys that are not going to mix, and you would expect a solid to form, which is, we'll get the S symbol for solid. So let's take a look at some of these rules. Anybody in group 1 on the periodic table, if you see it in a formula, will be soluble no matter what. So they will always be aqueous. There are no exceptions, which means as soon as you see that in a formula, you could pretty much put aqueous next to it. You should know it's a solution. There's not going to be a problem. Same thing with ammonium. And if you see that in a formula, it will be soluble. And once again, there are no exceptions, which means as soon as you see that, you know it's going to be aqueous. It's going to be a solution, no solid. Same thing with nitrate, will be soluble. And again, there are no exceptions, which means as soon as you see that in a formula, you will know that it's going to be aqueous. If you have chloride, bromide, or iodide, they will be soluble. which means they will be aqueous. But there are some exceptions, which means that if you have either chloride, bromide, or iodide, and they're hooked up with silver, lead, and that's mercury 1, if they're hooked up with any of those three, and it's chloride, bromide, or iodide, they will not be soluble. They will be the opposite, which means they will be insoluble, and they will end up being solids, and they will form a solid. If you look at sulfates, sulfates are typically soluble, except for these guys, which means if you have any of these guys with sulfate, they will be insoluble and be a solid. They'll be the opposite. Carbonates are typically solids, insoluble, unless it's with somebody in group 1 or ammonium, which means it will be soluble. It's basically the same rule as the top one. Phosphates will typically be insoluble, except if it's hooked up with somebody in group 1 or ammonium, which will make it aqueous. And lastly, hydroxide are typically insoluble unless it's kind of somebody hooked up with group 1 or some of these guys here, which would then make it aqueous. So to show you how this works, for example, we took some silver nitrate and we remix it with some potassium chloride here. It's a double displacement reaction, going to give us some silver chloride plus some potassium nitrate. So we could use the solubility rules here to help us decide what's going to be a solid and what is not going to be a solid. So let's take a look and see how we could do this. So you may not find silver on the list, but you will find nitrate, and nitrate is right about there. And nitrate is soluble in everything, and there is no exception. So as soon as you see nitrate in that formula, you know that this is going to be a solution. No solid is going to get the aqueous symbol. When you come over here to potassium, that is group 1 on the periodic table, which is right here. That is soluble in everything. There is no exception, which means as soon as you see the potassium in the formula, I also know that this is going to be aqueous with no worries. I come over here, bless you, the silver. May not find it on the left-hand side, but I do find chloride. What is the deal with chlorides? Chlorides are soluble, except when it's hooked up with silver, which is the case in this case. So it is usually soluble, but this is an exception. So actually, this would make a solid in this case because of the solubility rules. You might have done it in one of the experiments. It's like a white solid that forms, and that usually stains your skin as well. So if we come over here to potassium, that's pretty much as far as we need to go. It's group 1. It's going to be soluble in everything. You could also look at nitrate in this case, which is also soluble in everything. So this would be soluble. So in this reaction here, we would expect a solid to form when the silver ion goes and finds the chloride ion. So what happens in this case is the silver nitrate supplies silver ions and nitrates. They're floating around along with the potassium ion and the chloride ions. And these two guys decide we would like to make a solid, basically, and they'll drop out of the solution. The potassium, the nitrate, still floating around at the end. They're still in the solution, floating around as ions. It's just the silver and the chloride coming together and dropping out of solution. Question on that there? Why don't you try one here? Let's do one I just did this afternoon. Let's see, or this morning. Let's do lead to nitrate. Plus sodium iodide. Makes a little lead 2 iodide and a little sodium nitrate. We'll do. Okay, let's take a look. So again, you may not be able to find both things on the table, but you should at least be able to find one thing. So we may not be able to find the lead, but nitrate is definitely in there. So as we saw earlier, nitrate is soluble in everything. So that's really as far as you need to look. I know that this is going to be aqueous in a solution. When I come to the next one, I hit sodium off the front here, and sodium is group number 1, which means it also is soluble in everything. There's no exception. You don't even need to go any further than that. Coming here, lead I may not see, but I do see I, which is iodide. It is soluble in everything except for silver, lead, and mercury, and this happens to be one of the exceptions. So instead of being soluble in this case, because it is hooked up with lead, it becomes the opposite, and we would expect that guy to become a solid in that case. Any questions on that? That is why over here, this guy is not a solid because it's not hooked up with silver, lead, or mercury. It's hooked up with sodium. So that's why this guy's not a solid. But when it does hook up with one of those three, it becomes a solid, the I. Coming over here to sodium, that really is as far as we need to go. You could also look at nitrate, which also gives you the same answer. They are both soluble in everything. So in this case, if you mix these together, you would expect this lovely yellow solid to form, which I saw this morning all day. And you would get a solid because of that. Again, in this case, started out with the guys on the left, you got all those 4 ions floating around. The lead and the I will come together as they're attracted to each other, and they basically will come together. And when they do, they drop out of the solution part and become a solid, a little yellow solid that forms. Any questions on solubility rules? It would probably be provided for you, I suppose. Yes. There that is as well, in case I missed it. All right, so continuing on here with this idea of solubility. As I mentioned before, that is a really important idea of like dissolves like. So things with similar sort of interactions will be soluble in each other. The solubility of a solute in a solvent depends on temperature. Usually, if you raise the temperature, you could get more solid to dissolve in a liquid. They sometimes tell you that if you're trying to dissolve something and it's not dissolving, just kind of warm it up a little bit, and that increases the solubility typically of a solid in a liquid. And that's because when you warm it up, you're actually adding energy. Yeah, so that helps the whole process there to get more of it to start to dissolve as well. Lower temperature, we have a larger solubility of a gas in a liquid, and that is because if I have a liquid and I got a gas molecule in it, represented by that wonderful circle there. If it is a low temperature, my gas molecule is moving fast or slow? Slow, which means if he's in the water and he's moving slow, he's going to stay in there a lot longer, right? Than if it was a higher temperature, would bounce right out, right? So it will stay mixed for longer because of that lower temperature. The solubility of gases depends on pressures. The higher the pressure, the larger the solubility of gas. We call that Henry's law. That's the soda can law, right? Before you pop a soda can, you have CO2 dissolved in your soda part, right? When you pop it, or before you pop, it's under high pressure, so you have a lot of the CO2 dissolved in the liquid part. When you pop the lid to go drink it, you see what come out of the hole. It starts to fizz, right? That is the escape route of your CO2, right? You also lowered the pressure. It's now going to be less soluble in the liquid part. The CO2 goes out. You walk away from your can of soda. You come back, it tastes flat because all your CO2 just left it, right? And that's why it becomes flat as when you do that. These are good life lessons, I suppose. So when we talk about solution composition, there's a couple of ways that we describe solutions as well. And one way that we describe solutions is a saturated solution. And when you have a saturated solution, you have pretty much the maximum amount of solute that will dissolve at a given temperature. So solubility is dependent on temperature. So at a particular temperature, there's only so much that you could get to dissolve. I like an example of like, you order something at a restaurant, you put a couple of packets of sugar right into your water, it will dissolve. You got really slow service, so you take all the sugar you can find and keep piling it into your cup. The waitress or waiter loves you for that, right? As well as you do that. But at some point, it's not going to dissolve, right? It's going to start to build up on the bottom. Or you take the Costco size sugar there and dump it in there. It's going to not dissolve. But a saturated solution is one where you pretty much have hit the point of I can't get any more to dissolve at that point. So once you hit the saturated solution or the saturation point, that's a solution where you got the maximum amount of that solute that will dissolve at that given temperature. Pretty much if you continue to add more past that point, It's just going to, again, pile up on the bottom. It has no way to dissolve it. What's the opposite? The opposite is an unsaturated solution. In an unsaturated solution, you haven't pretty much hit that point yet. So you could continue to put more solid in there. It will continue to dissolve, and it will continue to dissolve until I hit what? A saturated solution, basically, right? Or a saturation point. So it'll continue to dissolve until you hit the saturation point or a saturated solution. And at that point, obviously, you can't get any more to dissolve. Any questions on that there? Other ways we describe solutions is concentrated or dilute. A lot of times a stock solution is how they normally come, which means it contains a relatively large amount of solute. Big M, which is molarity, which is a common unit of concentration that we'll talk about. The higher that number is, the more concentrated it is, the more careful you should be. If you see a big number next to it, like 18, that's like burn your hands off. It's like strong, yes. But most of the time, the solutions that you use in class and stuff is a dilute solution. And we usually will add more solvent to it, and it will actually make it a more dilute solution. And it has a relatively small amount of solute. So the example of that would be you get the giant beverage there with ice before you come to class. You leave it in your car. After a long day at school, you go back to your car. All the ice is melted, right? You try it. You taste it. You do. You go, how bad could it be? And then you taste it and go, maybe that wasn't the best choice. We have to live by our decisions. But it doesn't taste as strong as it does, right, when you first got it. And that's because obviously all the ice is melted, a lot more water has come into it, and you just diluted it down, right? So you have less of your syrup and all that good stuff that makes it taste much better than it did after a long day in the hot car. But you still go for it because you got to go for it, I think. All right, so let's talk about a couple of things here to finish up on, which are electrolytes. And electrolytes are substances that when they go for a swim, that is the chemistry terminology there. I'm going to actually write it. When they go for a swim, you'll find that in all the finer chemistry textbooks. When they go for a swim, they basically will break apart into ions. And because they break apart into ions, they're able to conduct electricity. And it's those presence of those ions. The presence of those ions will help sort of complete the circuit and allow it to conduct electricity. There's some different types of electrolytes. There are strong electrolytes. And a strong electrolyte is a really good conductor of electricity. When it is in solution, it will 100% break apart into ions. So for example, if you did have a sodium chloride solution, in solution, that guy is really 100% sodium ions that are floating around in there and chloride ions floating around in there. You have none of these guys still together in that solution. So you basically have a solution there that has a ton of ions basically freely floating around in that solution. Because of the presence of all of those ions, it will conduct electricity really, really well. I will just write light bulb because one time I tried to draw it and it wasn't so great. So you have a light bulb connected to some electrodes, which maybe you're doing in the lab this week. And if you put that into a strong electrolyte solution, it will be very bright, the light bulb. It will go off very, very bright because it's able to conduct electricity really, really well. And that's because there's a ton of ions floating around in that solution. Now, there are electrolytes which are weak electrolytes. And weak electrolytes mainly stay together. But will produce some ions. So for example, hydrofluoric acid is an example of a weak electrolyte. It will break apart a little bit into H plus and F minus. You will have a few of these ions in solution, but you will mainly have this guy still together, which means when you look at this solution, you mainly have the HF guy still floating around, but you do have a little bit of H plus, you got a little bit of F minus floating around. So since it's able to produce a little bit of ions floating around in solution, it can still conduct electricity. Nowhere near as good as a strong electrolyte that has a ton of ions floating around. This guy's got a few ions floating around. If you put your light bulb in there, you will get a dim light bulb. It will still turn on, but it looks like it's dying. Yeah, it'll be kind of really dim. And that is an example of a weak electrolyte. Because there's still ions present, it's able to conduct electricity a little bit, but nowhere near that. The way you can recognize it in formula form is you will see these reversible arrows, and these reversible arrows indicate that this reaction has a forward direction and a reverse direction. And eventually it'll reach equilibrium where they're going in the same rate, backwards and forwards. So that's a real key, is to know if you see an equation with arrows heading in both directions, it's a weak electrolyte, and you should conduct electricity a little bit, but not very, very well. But it'll still be able to conduct it. Any questions on a weak electrolyte? That is different than the arrow we see in a strong electrolyte. It is a one-way arrow where everybody's dumping off to the product side. We're making a ton of ions in that particular solution. Any question on those two? The last type of electrolyte, which I guess is an electrolyte, I'll use this as an example, is a non-electrolyte. And a non-electrolyte will dissolve in solution, but it will not form any ions. And because it does not form any ions, there's no ions there to conduct electricity. So it does not conduct electricity. So as you can see here, sugar is an example of that. You can take some solid sugar, you can get it to dissolve, but it will not break apart because sugar's carbon, hydrogen, and oxygen is covalently bonded together. Yes. It will dissolve in solution, but not form any ions. And because, again, it's the key there is there's no ions, so it will not be able to conduct electricity. And sugar, although it will dissolve, will not produce any ions, it will not conduct electricity. No light bulb. Weak electrolyte there, dim light bulb, strong electrolyte, bright light bulb. Pure water, is it a good conductor of electricity? Pure water is a bad conductor of electricity, yeah, because it's just H2O, no ions. Let me be very clear, the water comes out of your faucet at home and sink is not pure water. They put ions in there. You will electrocute yourself if you blow dry your hair in the shower. Yeah, so don't do that. Also good life advice as well. But if you have pure water, just H2O, because it's covalently bonded, there's no ions in that solution or that bottle there of water, it would actually be a bad conductor of electricity. Any questions on that? All right, we'll wrap it up.